Hello everyone, welcome to the class of Calculus 3. Today we are moving to the topic of triple integrals in section 5.4. I suppose we understand well the ordinary integrals, like in terms of x, in terms of y, they can be considered as integral along the x-axis or the integral along the y-axis, along a horizontal line or a vertical line. And then a double integral, it can be considered as an integral over a region. And then accordingly, a triple integral really should be considered as an integral over a solid. At this moment, let's say, make it simple. The solid we are considering here, it is a rectangular box. It is a rectangular box. So accordingly, it can be described in a very simple algebraic way. Okay, the solid in the three-dimensional space, so there's x, y, and z here. X, y, and z, three variables. Each, it is bounded by a pair of fixed constants. X running from a to b, y is running from c to d, and z is running from e to f. And then the triple integral over a rectangular box, let's say we can consider this function of three variables as a density. Okay, the thing is the solid of this rectangular box, it's not of uniform density, but we do know the density distribution. So each time if we multiply this function by a small volume, that will tell us the mass of this little cube here. And then if we add all the mass of all those little cubes together, keep in mind that this is the cube. It is a small part of the rectangular box. Okay, we have many along the x direction, y direction, and the z direction. So indeed, this time when we add all of them together, we could have the total mass of the entire rectangular box. And I use the sigma notation to denote the situation. And indeed, this is still a Riemann sum, and some people may call this a triple Riemann sum. And then imagine if each solid it is small, tiny enough, and then we do have infinite number of them along the x direction, y direction, and the z direction. Accordingly, we write this limit as a triple integral. And usually, the way to calculate a triple integral, we really don't bother about this definition. It's too complicated. But we do have somewhat efficient, relative easy way to evaluate a triple integral. So this is the so-called Fubini's theorem, a triple integral over a rectangular box, okay. And again, such a triple integral can be considered as the total mass of a solid. This function f should be considered a density function. So the triple integral will tell us the total volume. And the Fubini's theorem says, well, first of all, to evaluate this triple integral, you really would have to consider like delta x, that's dx, delta y, that's dy, dz in this fashion. And this is an iterated integral. And in the order of x first, x matching a and b, then y, c and d, z it is for e and f. And then the interesting thing here that you may want to know, for triple integral over rectangular solid, basically there are 6 ways, because you can consider the combination of those 3 items, right? dx, dy, dz. There are 6 different combinations, 6 different combinations. So accordingly, a triple integral really can be evaluated in 6 ways. Okay, it is always in the fashion, let's say if this dx part, it will match the innermost. If dx goes first, it will match the innermost integral sign. And the dy match the inner integral, and the dz match the outer integral. And look at it in this case, dy is matching the innermost, dc it is matching the inner part, and the dx it is matching the out integral. So there are six ways. How about let's do one example quickly. This is the example I took from the textbook, and what we need to do here is just to evaluate a triple integral over a rectangular solid. Okay, the function it is x squared yc dv, and x running from -2 to 1, y is running from 0 to 3, z is from 1 to 5. And what I did, I considered this triple integral in the order of dc, dy, dx. And if you followed my lecture, follow this video, hopefully you got the idea. There are six ways. To save time, we're not going to go through all six ways. And there are two other ways on the textbook: dy, dx, dc, and the dx, dz, dy. I believe the textbook did both ways. And also I'm trying one more way. Okay. So I'm considering the triple integral in the order of dz, dy, dx. When we consider the integration in terms of z, x squared y is considered a constant. So really it is the integral antiderivative z, which is 1/2 z squared. And then we will have to replace z with 1 as the lower bound, and the z with 5 as the upper bound, then do a subtraction. So the inner part at this moment, when z is replaced with 5 and 1, this is 25, right? Minus 1, 24, divided by 2, that's 12. So I got a 12x squared y dy dx. Well, for triple integral, usually we start a point with x, y, z, all three variables. Then after evaluation, one round of evaluation, there are two variables left. So we do have x and y left here. And then we work with another round of integral according to the order. We chose in the beginning the inner integral, now it is the innermost. It is dy, we do this dy first. And like we did for dc, it's really the same rule. Antiderivative y, it is 1/2 y squared. 12 divided by 2, that's 6. So x squared y squared. Then replace y with the upper bound and the lower bound, taking the difference. Okay, so there's only the upper bound matters. The lower bound is 0. So 3 squared, 9. So that's a 54x squared. So in the last round, there's only about x, right? We're supposed to have a number for the triple integral. So in the last round, doing one more round of evaluation, I think this turned to be 18x cubed antiderivative. Antiderivative x squared, 1/3 x cubed. 54 divided by 3, that's 18. And in the end, I have the answer as 162. 162. And so this is the introduction part of the triple integral. The example we just talked about, it is from the textbook, and the textbook showed two other ways in different orders. And indeed, there could be 6 ways, 6 different ways, okay. But anyway, for a given triple integral, there should be a single answer. So this is what I got. Hopefully, this is the same number as on the textbook. Thank you for watching.